If one wants to calculate the scalar curvature, Ricci scalar of a Riemannian or pseudo Riemannian manifold, then one can either take the usual approach in which one first calculates Christoffel symbols, and then one calculates Riemann tensor, then Ricci tensor, and then Ricci scalar. And from Ricci tensor we can calculate Ricci scalar, which is the scalar curvature. However, there is one another way to calculate the Ricci scalar, and this method uses comparison of infinitesimal volume elements. If we are given a Riemannian manifold M, then to calculate its Ricci scalar at a point P, we can do the following. We take a ball of radius epsilon at point P, where the distance is of course measured using the metric on M. So at point P we consider a ball of radius epsilon at this point P, and then we calculate its volume. So we take the volume of this ball of radius epsilon, which is contained in this manifold M, and we take the ratio of this volume, we divide this volume with volume of ball of same radius at, say, origin in the Euclidean space. Here n is the dimension of the manifold. Then to first order in epsilon, 0th order in epsilon, this ratio will give 1. There will no term corresponding to the first order, but in the second order term we will have S epsilon square divided by 6 n plus 2. Here S is Ricci scalar, and then we'll have higher order terms. So using this method we can calculate the Ricci scalar of a Riemannian manifold. All we have to do is take a ball of radius epsilon. If we want to calculate the Ricci scalar at a point P, then we take a ball of radius epsilon at that point, we calculate its volume, we take the ratio of this volume and the volume of a ball of same radius in the Euclidean space, and then we take its series expansion and find its coefficient of the epsilon square term in that series expansion. Then the coefficient of the epsilon square term will be Ricci scalar divided by 6 n plus 2. For example, if we take n is equal to 2-dimensional manifold, and we specifically take the 2 sphere, so in case of a 2 sphere, it's a 2-dimensional manifold, so volume will be replaced by area, by volume. Volume and area are same thing in two-dimensional space. So suppose we have this is our sphere. Suppose of radius r, capital R. This is North Pole, this is South Pole. Now the metric of this sphere is homogeneous. This is a everywhere it's the same, so we can calculate Ricci scalar at any point on this sphere. So let us suppose we take our point to be North Pole. So at this North Pole we take a ball of radius epsilon. So this will be a disk of radius epsilon. This is our disk of radius epsilon. We want to calculate its area of this disk. This is our two-dimensional sphere, and at the North Pole we are taking a disk of radius epsilon. This is radius capital R. Radius of this sphere is capital R, and this epsilon is the radius of the disk which we are taking to be centered at the North Pole. Now the area of this disk can be easily calculated. If we take a strip, take a small strip inside this disk, which say makes an angle theta. Here we have angle theta. Then the area of this small strip, if this is d theta, then this width of this strip will be d theta times r and d theta, and its circumference will be, since this is r, capital R, so circumference will be that is the length of this strip will be r sine theta, 2 pi r sine theta. So area of this small strip will be dA, circumference, which is 2 pi r sine theta times r d theta, so it will be 2 pi r square sine theta d theta. Therefore the area of this disk of radius epsilon will be 2 pi r square sine theta d theta, theta from 0 to when this radius is epsilon, then this angle will be epsilon by r. So theta goes from 0 to epsilon by r, and this is equal to 2 pi r square 1 minus cos of epsilon by r. So this is the area of a disk of radius epsilon which is centered at the north pole. And since sphere is a homogeneous manifold, it's everywhere, its geometric properties are same everywhere, so this is true for any disk of radius epsilon, irrespective of where it is centered. So if we take a disk of same radius epsilon in the Euclidean space, so this is the area of disk of radius epsilon in on a two sphere. This is on a two sphere, but if we take a disk of radius epsilon in Euclidean space, then its area will be of course pi epsilon square. So the ratio of a sphere divided by a Euclidean, a sphere divided by a Euclidean will be 2 pi r square 1 minus cos of epsilon by r divided by pi epsilon square. And we want to expand it in a series and take the coefficient of epsilon square. And in two space, coefficient of epsilon square must be s divided by 6 times 4, which is s divided by 24, where s is Ricci scalar. So the coefficient of epsilon square must be s by 24 for the case of two sphere. If we expand it in epsilon, first of all pi cancels pi, so we are left with 2r square by epsilon square 1 minus cos of x. Series for the cos of x is given as 1 minus x square by 2 plus x4 by 4 factorial, and 4 factorial is 12. 4 factorial is 24. And higher order terms. So we'll have 1 minus epsilon square by 2r square plus epsilon 4 by 24 r to the power 4, and then higher order terms. So we will have 2 r square by epsilon square. 1 will be cancelled by this one, so we'll be left with epsilon square by 2r square minus epsilon 4 by 24 r4, and then higher order terms. So now we'll get 2r square will cancel 2r square, epsilon square will cancel epsilon square, so we'll be left with 1. The first term is 1, and then the second term is epsilon square by 12 r square. So the plus higher order terms. So the coefficient of epsilon square is, sign is minus. Here also we had a minus sign. With negative sign, this should be s by 24 when n is 2. The dimension of the sphere is 2, so it should be s by 24. So s by 24 is equal to 1 by 12 r square. this 1 by 12 r square, which is the coefficient of epsilon square, should be Ricci scalar divided by 24. So this implies that Ricci scalar of the two sphere is 2 by r square, where r is the radius of the sphere. So this is our Ricci scalar for the case of two-dimensional sphere of radius r. And we have used this method of comparison of areas for calculation of this Ricci scalar. This is true in general for any n-dimensional Euclidean n-dimensional Riemannian manifold by this formula. Calculate the volume of a ball of radius epsilon, small radius epsilon, centered at a point P, and take its ratio divided by the ball of the same radius in Euclidean space, volume of the ball of same radius in Euclidean space, and then its series expansion in epsilon must be of this form, and the coefficient of epsilon square term must be Ricci scalar divided by 6n plus 2. For the case of two sphere, it was s by 24, and this coefficient, we calculated this coefficient, and it was coming out to be 1 by 12 r square. So our Ricci scalar by comparison comes out to be 2 by r square.